Thank you for spending the time listening to this virtual presentation entitled Achieve Your Vision with Time-of-Flight 3D Sensors and Cameras. My name is Tim Dodd. I'm Product Sales Manager at IFM Electronic. I have over 23 years supplying solutions for automation into many industries and many environments. The presentation is going to look at 3D imaging as a solution for automation, in particular 3D time-of-flight. But first we're going to look at the sort of techniques or what is technology that's available for creating 3D vision in automation at the moment. Have a look at 3D v 2D, and then we're going to look at applying 3D time-of-flight technology to real-world applications. So if we look at the options available to you when you say, right, I need a 3D image for my my automation application, there's four ways of creating that image. So we look at LiDAR at the top there, laser imaging detection and ranging. So we fire a laser at an object, we take multiple measurements, we build up a 3D image of that object over a period of time. We then have structured light, so we project a light pattern onto the object. Then we use a camera which is offset from the projector to look at the deflections in the light pattern, and again we build up a 3D image of the object. Stereo vision, we take two images and we compare it from two different points, like the human eye, and then we compare the differences between the two images to create our 3D image. With time-of-flight technology, although we're using triangulation, which is basically what the three use, we the way it works is completely different, and it allows us to capture a whole scene in one frame rather than having to take multiple measurement points and building up an image. So it's quicker to build a 3D image up using time-of-flight technology than it is the other three, for instance. Also, the technology involved is a lot less complex. So there's four technologies. How do I choose between them? So in a nutshell, if you need sub-millimeter accuracy and time is not of great importance to you, then LiDAR and structured light technologies and line scanners are the way ahead. They give you by far the better accuracy for a start off. The offset to that is the cost of the technology and the time to create the 3D image increases, and therefore there's an overall cost increase in the application usually, and your return on investment can take longer. With the time-of-flight technology, as I've already said, you can capture the scene in one frame, so it's quicker and it's not as complex technology-wise. So to create the 3D image, it doesn't require as much processing. Therefore, the overall cost of the package and the installation, etc., is a lot cheaper. However, you are looking at accuracy of only a few millimeters, not sub-millimeter. So if accuracy is what you need, LiDAR, structured light, line scanners. If it's not, and you can live with a few millimeters accuracy, then time-of-flight technology may be the way to go. You then get asked the question about when 3D versus 2D. So 2D technology has been around a long time, and we've all had experiences of using 2D technology, and we know the importance of lighting. We also know the effect that change of colour can have in certain applications, because basically what we're after is an image with good contrast to allow us to pick out what we want. If you look at some of the applications we've been doing with 2D vision over the time, it may be that we can now apply 3D time-of-flight technology to achieve the same thing, but without the concerns about changing colour or even the effect of ambient lighting. So we may not need a light box, for instance. Things I'm thinking about there is maybe holes in an object or holes of a certain size. It may be that all you need to know is the hole is there. You don't need to know what size it is. Or you only need to know there's 10 holes, but you don't need to know they're all 10 millimeters. So 3D time-of-flight will do that very easily, but give you a robust solution with a lot less extra work and maybe a light box, etc., than you would do with a 2D vision. So it may just be a case of having a look again at what the applications you're currently doing and seeing whether you can apply 3D technology to that application to give you a simpler but still robust solution to achieve what you want. So if we start looking at the hardware, I've kind of split it in two, sensors and cameras. What do I mean by a sensor? So a sensor to me is where the manufacturer has took a lot of the legwork out for you. So you have a 3D image being generated, you need to apply algorithms to that to get it to do something useful. With a sensor, these are built in either to the firmware or there's an application suite created by the manufacturer for, say, level or volume or whatever it might be, and you can just change the parameters that you want to change. So if it's volume, for instance, then you could set your basic switch point, if you like, on volume, and that's all you need to do. You don't need to do any more processing. So it's all very straightforward, very easy, and it's very quickly implemented as part of your automation solution. A camera, 3D time-of-flight camera, however, you need to do a lot more work with it. So we're going to give you the 3D point cloud. We might, we usually will allow you to we'll change the frame rate, we'll change the exposure, and we'll change the interface to the PC or the PLC. But then it's going to be a raw streaming data of the 3D point cloud where you apply your own own algorithms to it. There's advantages to that if you are an OEM and you're making guided vehicles, or you're making robotic milking machines, or there's, your customers ask you to look at a very specific application where the standard sort of volume, level, distance type applications written by the manufacturer just aren't going to be good enough for you. So you then move to a camera solution to allow you to do that. But this is few and far between applications. Most people can use 3D time-of-flight technology and use it in a sensor and get a very successful solution. So have a look at how we do 3D time-of-flight then. So there's two ways, pulsed or continuous wave. Pulsed, often called direct, is where we send a short pulse of light out, just a few nanoseconds long, and then we measure how much light we get back. There's quite a lot of technology or sort of clever timings and processing required to get the accuracy you need to get this millimeter accuracy through that technology or through that method. So what you'll find in the marketplace is a lot of people now use continuous wave or indirect time of flight. So this is where we send out a modulated light form, and we actually measure the phase shift instead of measuring how much you receive. We look at phase shift. It's a lot easier to implement. The technology required in the sensor itself is a lot simpler, therefore the cost comes down, but we still achieve the accuracy and we still achieve the high speed that we were after when we set off on looking at this technology. So hopefully now we're looking down and you're thinking, yep, I like the idea of this, but what do I need to know before I start looking at time of flight in my application? So when you look at the websites and go through making choice of supplier, you'll see that we quote things like resolution. So that's the size of array of receivers inside the camera. We define its working range, so 0.3 to 5 meters. It's never 0 to something, because with time of flight there's a sort of like dead zone where the returning light is that quick that we can't actually process it reliably. So we set ourselves a safety barrier, if you like, and in this example here 0.3. So from 0.3 to 5 meters the sensor will work. And then we give you angle of aperture of the lens, and that means that you can then work out what your field of view is based at whatever distance to the object it is. We just pop back to the sort of resolution side of things. So the resolution is fixed, pixels, the array size is the same. Field of view is also fixed at a certain distance. And then what we need for reliable detection is we need a number of pixels, say 9 pixels, to hit an object for us to be able to reliably analyze that object or feature. So as you move further away from the object, the pixels spread out effectively because of the aperture of the lens, so less pixels are hitting the object. So you just need to bear that in mind, that an object that's 100 mil cubed, you may need to be within 2 meters of it to pick it up reliably, and if you're at 5 meters, we can't pick it up reliably. So you just need to bear in mind that that is what's happening with the camera. We then need to look at the fact that we have a shadow cast by objects. So in the example here, I've got a 3D camera looking down upon a metal block, for instance, and we're using a volume application that was built in by the manufacturer. The volume of that object will look bigger from one camera because of those shadow areas, which are the light grey areas. If you want to get rid of that shadow, you need to put multiple cameras in and start combining images. But in reality, in most applications, we don't need to worry about it. You just need to know that the actual volume the camera will see will be larger probably than the actual true volume of the object you're trying to look at, but it will be repeatable. So you'll be able to work that out in your calculations in your PLC processing. couple of other things pointed there as well. If you've got really shiny objects, they can overexpose because of the image, so you need to change the exposure time, or you maybe need to offset the camera a little bit so it's not looking directly down on the shiny object. And there are some materials that will absorb infrared and will look smaller in the scene than they actually are, but again, it'll be repeatably smaller. So if it's a 100mm diameter ball, it might always look like an 80mm diameter ball, but it will be repeatable. Again, it might seem obvious, but it's an optical device. So water, dust, fog, direct sunlight into the lens will have an effect on it. So you just need to be aware of it. There are some time-of-flight cameras out there which have been tuned for outdoor use. So if you are looking at applications that are kind of outdoorish or might be affected by real, sun off snow, for instance, then you need to look for the right camera from the right manufacturer to be able to do that. But in general, things like dust and water and fog will affect the image because we can't look through dust and fog to get to pick up an object. We've talked about the speed of time of flight via line scanning. So this is just a little simple animation which brings that point home in a very simple fashion. So we scan the object with a line scanner in a traditional manner. And then if we compare that against using a time-of-flight camera, and then combine the two together, so it's a little bit exaggerated, but as you can see, the idea is the time-of-flight camera captures the scene in one frame, and therefore it speeds the operation up. All those little seconds add up to save you time overall in the process. Let's look at cost v performance then very quickly. I've not put any pounds on here because depending on where you're looking, it depends what the costs are, but simple sensor is obviously going to be your cheapest solution, but it's very limited in what it can do. Your high accuracy line scanners and LiDAR are at the other end, very high performance, but also come with a cost add-on for that. And then your 3D time-of-flight cameras sit in the middle ground. They offer very, very good performance at a very reasonable price. So as I say, over the last 5-10 years, the price of the technology has really come down to a point where you can seriously consider it for your automation projects. Very quickly look at some use cases then. Now, I've sort of done sensors and cameras. So this is a sensor. Level in a bucket. Could be of dry goods, for instance. It's very good for dry goods. If you have dry goods which usually heap as you put them into a bucket, point level's not much use because it will only look at a point. Whereas if you put a 3D time of flight camera on it, or sensor on it, sorry, you can average that out, so you get a true level, a true look at what the level is in the bucket. Part missing. You could do this 2D, you could do this multiple sensors. If you do multiple sensors, multiple brackets, multiple cables, so it's costly. A time-of-flight sensor, do one camera, whole image, and also flexibility. If the product changes, you don't have to keep changing your photocells around or adding photocells, taking photocells away. And then the final one there, height orientation check. You could do a line scanner, and has been done with a line scanner or a LiDAR before, but in reality you just want to know is the bag, or in this case suitcase, the right size to go down the chute and in the right orientation. Time of flight sensor will do this, no problems at all, and it'll be far easier to set up, and the cost will be significantly reduced. Look at dimensioning. So just again, another animation showing a line scanner against a 3D camera, or sensor, sorry. So when it comes out, it's one of the boxes bigger. And really what we're trying to show here is that the both technologies can pick the problem up, but it's where in the operation you can pick the problem up early or late. So it's just about speed. And if someone throws a box in which is wrong, we can pick it up early because we have the time to do it because of the technology that we're using. This is a very common application, so palletizing or depalletizing. So here we're picking a layer and we leave a box behind. So we could, if we line scanned it, we could do that, or we're going to have multiple photocells looking down to check whether we've left something behind, or we use some other technology to check it. Time of flight sensor, take single frame, analyze the image. Is there something left? Yes or no? And then we can tell the robot there's something left, so be careful when you go to pick it up so we don't damage the gripper. Content verification, i.e. how much we've got in the box. Very simple application. As you see here, we're doing it with photocells. Problem with photocells is, or an array of photocells, is if the box size content changes, i.e. we go from 6 to 4 for instance, then we have to play around with the number of photocells, or we need to build some logic in there to say only use 1 to 4, not 1 to 6. So what we really could do with this is, if we're going to have this kind of production line where we are changing what's going down it, then if we use a time of flight sensor with a bit of intelligence on board, we can load a number of applications into it, and then if we change the product that's coming down, we just load the right application, and we don't have to change bracketry, we don't have to change the setup, and it just will work very simply. So it makes life a lot easier, certainly bottling lines where pack sizes might change. Now this is more of a camera application rather than a sensor application. So here we're just showing very simply that we've got a line scanner on a automatic guided forklift truck. Because of where the scanner's mounted, we have to move it up and down to see where the pockets are. If we use a time of flight camera in this case, we can take one image, don't need to move the forks, so that it just speeds up the whole operation basically. And again, it's an animation, so all right, we might have exaggerated a little bit, but basically it's you can get the idea that what we're trying to do is increase the picking time. Decrease the picking time, and therefore the operation, you can do more picks per minute, etc., etc. So final three, I'm going to show some images on the pallet detection system, the supermarket check-in and milking a cow. These are definite camera applications. You need to do some work on these and process them. You can't do them with a sensor in most cases. So images from the camera, from a 3D camera, is the kind of thing you're going to see. So these are your pixels. Then you apply your own algorithms to try and find these pockets and clean the image up, so you can end up with a very good image there, and it allows you then to apply that onto your vehicle and look at this application. Bossanova have used time of flight to do shelf check-in. So basically, this is a robot. It goes down the aisle, and they reckon they can check a shelf or a row of shelves and a whole aisle in 50% less time than a human would. And then it feeds directly back to, in this case, Walmart's stocking system, back warehouse, and the operators get told what to take to which shelf, how many are needed, down to 2 jars, 1 jar, etc. And it's using automation to speed up this process, and it's all because the time of flight technology is able to operate quick enough, and the cost is at the right price point. Final thing then, milking cows. So cows are live animals, and they're all different shapes and sizes. The automatic robot arm here needs to find the teat and put the suckers on to milk the cow, so we need to know where the teats are, and they've used, again, time of flight technology because of the speed. The quicker you can milk the cow, the quicker you can put the suckers on the teat and start milking the cow, the better for the cow. So it's all about speed in this application. Again, it's just another application where time of flight is proved its worth just on the speed side of things, because accuracy is not 100% required. So it's just another application. So that's me finished. Thank you very much for your time. Much appreciated. Hopefully you found it useful and informative, and hopefully next year we can see each other face to face at the UKEVA exhibition in 2022. For now, that's goodbye from me. Thank you.